Okay, so our procedure tells us to uh, identify the meshes. And so in this one, right, there's several closed circuits that we can draw. And this source, the resistor in the middle, the 2 ohm resistor, is called a bridge. And that makes that circuit a bridge circuit. And so even though it only has one source, it cannot be solved by circuit reduction techniques, because no two of those 5 resistors are in series or parallel with each other. So you can't reduce that resistance using series parallel rules. And so some method of, uh, you know, um, circuit analysis must be used in order to solve that. So KVL, KCL could be used. There's several closed loops that you can draw for that particular one. And so then, KVL becomes a bit messy because, well, you might consider there, depending on your approach, there's a lot of different unknowns that you could say, because the current through every resistor is different, and there's a total current. So does that mean there's 6 unknowns? You could get away with writing 3 KVL equations as long as you included every resistor. And so mesh analysis is a bit more systematic. And so let's think about the fact that there's a lot of closed loops that we could draw around here that includes the source. We could go this way. We could just go through the bottom here. And so when we think about what mesh analysis is, right, mesh analysis says that if a loop contains other meshes, then it's redundant and it's not a mesh. So for that particular circuit, there are 3 meshes. And this one, which includes the 1 ohm and the 5 ohm and the source, is a mesh. On the left half of this, we got a mesh. On the right half of this, we got a mesh. So that contains 3 meshes. And I'll call them 1, 2, and 3. And so, we have refrained from that a little bit, but our resistors don't have numbers here. All right, and we're asked to find the current in the 2 ohm resistor. So I'll call my meshes 1 and 2 and 3. Okay, so then assign mesh currents, right? So I1, which will go around this mesh, I2, which goes clockwise through this mesh, and I3, which goes clockwise around this mesh here. Okay, now next step is to indicate voltage drops. Okay, and so we have several shared resistors here, and so we got to be very careful about that. I1 goes through the 1 ohm resistor. It enters kind of the top left there. It's a negative down the bottom. So for the 5 ohm, it goes kind of up through, I guess, right? So positive here, negative here. Okay, so let's think about I2. I2 goes through the 6 ohm, and we put the polarities inside, even though that makes it a little bit messy, but we shouldn't really put them outside, right? Because there's no current over there. So the I2 goes down through the 2 ohm, so positive and negative. I2 kind of goes up, I guess we call that, through the 1 ohm, so positive down here on the bottom, negative here. Now for I3, right, it goes down through the 3 ohm. For the 5 ohm, down through there, so positive on the top here, negative on the bottom. It goes up through the 2 ohm, so positive here, negative here. Okay, so then our next step now will be to write our mesh equations. And start with mesh 1, lower left-hand corner. Okay, so we'll go around our loop here, comes to 1 ohm, which is a shared resistor. On the I1 side, we have negative 1 times I1. On the I2 side, it's a rise, so it's plus I2. Okay, so the next resistor is the 5 ohm. He's also shared. So on the I1 side, we have minus 5 I1. And on the other side of that one is mesh 3. So it's plus 5 I3. Okay, so now we continue around and we come to our 3-volt source and we're going from a negative to a positive. So that's plus 3 volts. That brings us back to our starting point. So that sum is equal to 0. So now you'll notice that this equation has our 3 variables in it. We have minus 6 times I1, the sum of the resistors that I1 passes through. Then we have plus I2 and plus 5 I3. We bring the 3 across the equal sign, negative 3. And we can call that equation 1. Now, very often I rewrite this equation 1 to make this coefficient here positive, but it's not necessary. So I'm not going to bother to do that today. I'm going to go ahead now and write my equation for mesh 2. And so, mesh 2. Now, what do you pick out for the lower left-hand corner of this, right? Well, I picked this one here. I'll mark it so that'll keep me aware of where I'm going to. Okay, so the first resistor is 6 ohms, and I2 passes through him only. So he's not shared or anything. So we got minus 6 times I2. Okay, so the next resistor is the center resistor here, the 2 ohm. And from an I2 point of view, it's a negative 2 I2. And that resistor is shared with mesh 3. So from the point of view of the second term in this, it's going to be plus 2 times I3. And okay, so the next resistor is our 1 ohm resistor. From the point of view of I2, we have negative 1 times I2. And he's shared with mesh 1, so it'll be plus 1 times I1. The source is not in that mesh, and so that sum now is equal to 0. Okay, so our terms for I2 should be negative the sum of the resistors that I2 passes through, which is indeed 9, according to our math we got here. And I guess I should be putting the term with I1 in it first. So we got I1, subtract 9 times, I should have I2 there, right? So I1, subtract 9 times I2. And plus 2 times I3, and that sum is equal to 0, and that is equation 2. Okay, so let's go with mesh 3 now. And again, now the lower left-hand corner, which I picked this one. And we go clockwise, and so the first resistor is the 2 ohm, and he's shared, so we got minus 2 times I3, and that resistor is shared with mesh 2, so plus 2 times the mesh 2 current, I2. The next resistor is the 3 ohm, and he's not shared, so only I3 through that one, so minus 3 times I3. And then we comes to the 5 ohm resistor, and of course he is shared, but with mesh 1, so minus 5 times I3, and because he's shared with, like we said, mesh 1, plus 5 times I1. That completes our loop. The source, again, not in that mesh, so the sum is equal to 0. And so we have now plus 5 times I1. All of our terms with I2 plus 2 times I2. And remember now, we should have the sum of the resistors that I3 passes through for the next one. And if you follow with the math, we got a -2, a -3, and a -5. So indeed, -10 times I3 and equal to 0. And that is equation 3. Now, next up is our solution to that. And so you'll notice that substitution now for this one could be a bit of work because all equations 1, 2, and 3 got all 3 variables in them. And so if we resort to our calculator solution, what we want to do here is say that we have our matrix of coefficients -6, 1, and 5. We have 1, -9, and 2. We have 5, 2, -10. It is the inverse of that matrix multiplied by the matrix of constants, -3, 0, and 0. And then that will be equal to the solution I1, I2, and I3. So if you put that into your calculator now, or if you solve by substitution, or if you solve by Cramer's rule, you should get exactly the same answer. And when I did it, I came up with 0.9885, 0.2299, and 0.5402. And so that is then the solution where by I1, 0.989 amps, shall we say, I2, 0.230 amps, and I3, 0.540 amps. Now, let's think about answering the question that we were asked. And the question that we were asked is to find Ix in the following circuit, which is the current through the 2 ohm. And remember now, the polarity is important here because Ix has been given as a direction from top to bottom, which means that I2 is positive in terms of Ix, I3 is negative in terms of Ix because opposite direction. And so what that means basically is that Ix is equal to I2 subtract I3. There's 2 mesh currents in that branch. I2 agrees with the direction of Ix, so it's positive. I3 is opposite to the direction of Ix, so negative. And so Ix is equal to I2 subtract I3. And we have then 0.2299 amps, I'll write that as, subtract 0.5402 amps. And so you'll notice that that turns out to have a negative value. So that current in that branch actually goes up, right? But that's no odds, because that's why we keep our negative sign to know our direction and so on. And so if we do the math on that quickly, 0.2299 subtract 0.5402, that gives us negative 0.3103 amps. And so again, the negative sign is important because the direction of Ix is specified, and we know that the current, that branch actually goes up. Okay, can we tell that from the circuit? Well, we know that I3 generates a current that goes this way, and it has a value of 0.9885 amps, and it comes up here and it divides. And so most of it probably goes this way, right? Because the 1 ohm resistor. Now there's a 5 over here, so the most there is 6, but you can't really add them up because the center branch says they're not in series. Up here you got 9. So yeah, you know, the current there probably goes up because this smaller resistor is going to have more current than the other ones, right? And so it's difficult to tell from your initial analysis from that what direction the current goes. Mesh analysis, you don't have to try to figure out the current directions. Assume them are clockwise. If any of them is counter to that, they'll show up negative in the solution, right? And so the direction for Ix is arbitrarily specified down. We get a negative number for it. We know that current goes up. And so that's fine, right? There's no problem there. Now, you can solve, again, this system of equations using substitution. Substitution with 3 variables in each equation like that is kind of trial and error. But, you know, it's not that hard to arrive at a solution. It takes a bit longer, of course, than the calculator solution. Using Cramer's rule is a bit more structured. And so however you do it, you should be able to come up with that solution.